Welcome to lecture number 17 for ECE 463 Modern Control, Servo Compensators with AC set points. Now, where we left off, if I want to track a constant set point, I add a servo compensator. What the servo compensator does is it integrates the difference between the output and the set point. Then I use full state feedback to place all 5 poles, the poles of the plant, plus one additional pole, the pole of the servo compensator, creating an augmented system. What the servo compensator does is it forces the output to track the set point, so I can track constant set points. It also allows you to reject a constant disturbance, and both track reject a disturbance and track a set point. Well, here's a problem for you. Suppose my set point or disturbance is not a constant. Suppose it's a sine wave. Does it still work? Well, the answer is going to be no. The servo compensator works because the gain at DC is infinity, so if the output is finite, the input has to be 0. If I change the frequency of the input, the gain is no longer infinity, so I can have a finite error to produce a finite output. So I no longer track the set point if the set point is a sinusoid. Similarly, I no longer reject the disturbance if the disturbance is a sine wave. So what do? How do I track a sine wave? Well, again, the servo compensator works by having the gain being infinity at the frequency of the set point as well as the frequency of the disturbance. If I change the servo compensator dynamics so that it has poles at the frequency of the set point, then the gain becomes infinity at that frequency. So that's kind of the solution. Change the servo compensator. Change it so that it now has poles or eigenvalues at the spectra of your set point. What that'll do is I will now have infinite gain at that frequency, meaning I will force the error to be 0 at that frequency. So Y will now track a sinusoidal set point. Similarly, I'll be able to reject a disturbance at that frequency. So the procedure is as follows. Given a plant, x dot equals ax plus bu, y equals cx, define a servo compensator. The servo compensator is now z dot is az times z plus bz times the difference, y minus r. Choose az so that the poles are at the frequency or the spectra of r. And choose bz so that I'm controllable. In state space then, the dynamics become as follows. I have my x dot is a times x plus b times u. Z dot is bz times c times x plus az times z plus bz times minus r. And then u, if I use full state feedback, is minus kx times x minus kz times z. Putting it together, the closed loop system then becomes z dot is a minus bkx minus bkz, az bzc. What? Okay, got those backwards. bzc, az, 0 minus bz. Okay, here we go. So z dot is bz times c times x plus az times z minus bz times r. So let's do a couple examples. Suppose I have the heat equation and I want to track a sine wave. Design a feedback control law so that I have a 2% settling time of 4 seconds and y goes to r. Now to do that, I'll create an augmented system, the plant plus the servo compensator. First step is to define a servo compensator that has poles at plus minus j2 radians per second because that's the frequency of the input. So here's an A matrix. Again, there's many different ways of representing it. Here's one where the poles are plus minus j2. And kind of one trick, the diagonal here is the real part of the pole. The off diagonal is the frequency. So this is 0 plus minus j2. Again, other ways of doing it. This is one of them. And the B matrix, if we make it 1, 1, is controllable. Anything that makes it controllable works. I'll now create the augmented system from before. This is what it looks like. So here's your A matrix. Here's a 0 matrix of appropriate dimensions, 4 by 2 in this case. BZ times C, so here's your B is 1, 1, and C picks off the fourth state. And there's AZ. My input for U is B and 0. Here's my B matrix and a 0 matrix. And my input for R is 0 minus BZ. So there's minus BZ and 0. So that's my augmented system. I'll now use pole placement to place the dominant pole at -1. And so the dominant pole is what I care about. The other ones, they're just faster than it somewhere. Arbitrarily, I just put the poles at -2, 3, 4, and 5 for the other poles. It's not that dominant, but we'll go with it for now. In MATLAB, the way you do that is input the plant. Here's your A, B, and C matrix. I'll add the servo compensator. This has poles at plus minus J2, and it's controllable. I'll now create the augmented system. Here's your A, a 4 by 2 zeros matrix, BZ times C, and AZ. So there's your augmented plant. Again, MATLAB, you're not going to see these dots lines. I just put that in there so you can see the different parts of it. And then B6 is your B matrix and 0. Now, using pole placement, I can place the poles. If I put the poles at -1, 2, 3, 4, 5, 6, here's your feedback gain, K6. The first 4 gains are Kx. The last 2 gains are Kz. And as a check, the closed loop poles are where I put them, so that works. Now to validate it, this is a little bit of a problem. In MATLAB, I can find the response to an impulse function. That's the MATLAB command impulse. I can find the response to a step input. That's the MATLAB command step. There is no MATLAB command for a sine wave input. So let's create a function that has the response to a generic input, like a sine wave. That's one of the strengths of MATLAB. It's very easy to create your own M files. I want a new step command that MATLAB doesn't have. I'm going to build it. So I'm going to create a function called step2. Completely original name. I like the name stepjake, but it's more letters to type, so we'll just call it step2. Step2 will have the state space system, A, B, C, and D, my time vector, my initial condition. Again, this we don't really care about right now, but later on when we get to observers, I will care about that. So just to plan ahead, I'll give it the initial condition x0, and my input. If U is 1, that's my step input. If U is sine of t, that's response to a sine wave at 1 radian per second. If U is cosine 2t, that's my input at 2 radians per second. Now, you'd think I have to use numerical integration, and that actually is kind of hard. One trick, this is actually what step command does in MATLAB, is I convert to discrete time. If I have a constant step size in my time vector, say every 10 milliseconds, I can form the discrete time version, where x of k plus 1 is a times x of k plus b times u of k. That's nice because I just iterate. Every time I multiply by a, I move forward in time 10 milliseconds. Do that a bunch of times, and I've got my time response. So discrete time is actually much, much easier to simulate in MATLAB. I don't have to use numerical integration. I don't have to sit there and worry about it's going to be Runge-Kutta of fourth order, third order, trapezoid rule. I can just say x of k plus 1 is a times x of k. Much, much easier. So this would be my simulation in MATLAB. To find the initial condition, that's where we need x0. And for k, going through the entire vector of t, calculate x of k plus 1 is a times x of k plus b times u of k. Repeat. To do that, I need to find out what is the discrete time version of my system. So in S-plane, x dot equals ax plus bu, y equals cx plus du. In the z-plane, zx, or x of k plus 1, is some matrix A of z times x plus bz times u of k. Y is cz times x of k plus dz times u of k. The conversion is as follows. Your discrete time A matrix is e to the at. That's the MATLAB command expm, matrix exponential. bz is approximately b times t. cz is c, dz is d. When I do that, this requires that my time vector has to have constant spacing. If the spacing is not constant, then my A matrix changes for each sample. So this program is going to be somewhat limited. It only works for constant spacing and time. Finally, to allow a sinusoidal input, assume T is a column vector defining the time at each point. U is also a column vector defining the input at each time point. For example, if I want the step response, if this is T, and notice I have even spacing, every time point is 10 milliseconds apart, U would just be 1s of T. So it's 1 for all time point, that's my step response. If I want the response to a 5 radian per second sine wave, then instead I make U equal to sine of 5t and input it to my step 2 command. So this is the actual code for step 2. There's my calling function. I'm going to pass A, B, C, D, time, initial condition U, return Y. My sampling size T is the difference between the first two time points. It assumes it's going to be equal spacing from then on. My discrete time AZ is matrix exponential e to the AT. BZ is roughly B times T. There's my initial condition, and then I sweep. For the first time point, Y equals CX plus D times U. And from then on, I just keep iterating. And what this does right here, the BZ times U, if I have, say, 3 separate inputs, B is a 4x3 matrix, U will be my 3 column vectors. The first column is U1, the second column is U2, third column is U3. So this pulls off the column, the ith point of the column for each one. And I got to transpose it because if B is a 4x3 matrix, U's got to be 3x1 matrix. So I take that, the ith row, flip it to make the correct dimensions. Basically, you need a transpose to get this to work. And U, each column of U corresponds to each input. Here I only have a single input, U is just a column vector. So that's the matrix or MATLAB command step 2. Once I create it, I can now use it. Find the response to a sine wave. So now that I have that, let's design a servo compensator for the heat equation and have it track a 2 radian per second sine wave. So I input the plant, input the servo compensator. This is a plant with a pole at plus minus J2 that's controllable. Create the augmented system. Here's my A matrix, B with respect to U, B with respect to R. My output matrix. Find the feedback gains K6. And then I want to simulate. Time goes from 0 to 10 seconds. X0, I'm going to assume 0 initial conditions. That'll change in a later lecture when we get to observers. And my set point is sine of 2t. I now take the step command. This is step 2 or step 3. I'm actually copied it 2 different times. Step 2 and step 3, same function. Here's my closed loop A matrix, A minus BK. This actually has your this has your Kx and Kz, which fits together the augmented system to include them both. Take the step response with respect to R. That's what I want to look at, the output, my time points, 0 initial conditions, and my input R is sine of 2t. And I'll plot the output along with the set points in red, and here's what you get. The set points in red is a 2 radian per second sine wave. The output is tracking it. So the servo compensator worked. I tracked a set point at 2 radians per second. Suppose I want to find out what happens if I have a disturbance at 2 radians per second. In that case, I will have my disturbance being sine of 2t. My B matrix becomes the B matrix with respect to U, which is my disturbance input. Repeat and plot, and here's what you get. I've got a disturbance that's amplitude 1 at 2 radians per second. Here's the output. I multiply by 500 so you can see it. And notice that it's rejecting the disturbance at 2 radians per second. So again, that also works. I track a set point at 2 radians per second. I reject a disturbance at 2 radians per second. Suppose I have both. I have a set point at 2 radians per second. I have a disturbance at 2 radians per second. One's sine, one's cosine. Servo doesn't care. Just 2 radians per second. Can I do both? Can I track a set point and reject a disturbance? And the answer is yep. So here I see the disturbance in green, the set point in red, the output in blue. Again, I track the set point, reject a disturbance. One thing to note, however, is this works as long as I'm at 2 radians per second. If I change the frequency and make it 1 radian per second, it no longer works. If I want to track 1 radian per second, that's a complete redesign. And we'll see that in just a little bit. Let's do a couple examples. Let's try the ball and beam system. With the ball and beam system, it'd be the same idea. I create the augmented system, and actually let me show you that in MATLAB. So in MATLAB, here we are. Doing the ball and beam system. So there's my A matrix for the ball and beam system. The B matrix is right here. Do the servo compensator, that's these dynamics, and create the augmented system. So here's the A matrix for the ball and beam system, a zeros matrix, BZ times C, and AZ. Find the feedback gains, and we put the poles at -1, 3, 3.1, 3.2, 3.3. I get my feedback gains, kind of big. Those look kind of big. One, 2, 3, 4, 5, 6. Okay. Those are still big. If we go with it. There's your feedback gains. That's Kx. So go into the ball and beam system. Here's my Kx. Put it right here. Kz. The last two gains right here. Get copied over right here. And I'm going to leave this alone because I checked this to make it, and it works. So I don't want to change it too much. I now add the servo states. I've got two servo states, initially at 0, 0. My set point is 2 radians per second. My control law is minus kz times z minus kx times x. Beam dynamics don't change. I add this guy right here. That's my servo compensator. Z dot is az times z plus bz times the difference, y minus reference. Integrate x, integrate z, and repeat. What that looks like is as follows. My set point is going back and forth at 2 radians per second. It's trying to figure out what the input needs to be to track a 2 radian per second set point. And eventually it figures it out. Voila. That's if my input is sine. Let's try cosine. And it tracks cosine. So there, I'm tracking a constant set point. Suppose I have a sinusoidal disturbance. A couple ways to do that. One way is like this. So here I have a disturbance on U. Can I track the set point in spite of that disturbance? And yep, sure enough I can. So again, the servo compensator is doing exactly what I expected. I can track a 2 rating per second set point. I can reject a 2 rating per second disturbance. Another way to do a disturbance, let's change the mass. Make the mass 1.1 kilogram. As the ball rolls back and forth, save, beam, save, run. There we go. As the ball rolls back and forth, gravity is now twisting it left, twisting it right, twisting it left. I'll have a sinusoidal disturbance. Again, it's working. I am rejecting the extra mass, causing a sinusoidal disturbance. So it kind of does everything I want. As I mentioned, if I change the frequency, it no longer works. Let's make this 1 rating per second. See what happens. Again, it's trying to go at 2 ratings per second, and it's having a hard time because that's not the frequency of the input. If I want to track a 1 rating per second set point, that's a complete redesign. So that's the ball and beam system. Let's try a cart and pendulum system. The cart and pendulum system is the same idea. If I can find MATLAB. Come on, puppy dog. There we go. So there's the cart, A matrix, B matrix. Create the augmented system. You have the carts, A, B, C, D. Make sure I got the right one. Yep, this is the cart and pendulum system. If the poles are complex, I've got the gantry system. Feedback gains. Put the poles wherever you want. Here, put the dominant pole at -1. I get my 4 feedback gains. Here's Kx. There's Kz. Now go back to the cart program. I'll have my feedback gain Kx, Kz. My servo compensator has poles at plus minus J2, so that's your 0, 2, minus 2, 0, 1, 1, so it's controllable. Add the servo states. I've got 2 of them. Now the control law is Kz times Z minus Kx times X. The servo dynamics minus Z dot is AZ times Z plus BZ times Y minus reference. Integrate X, integrate Z, repeat. And here's what this looks like. Just the dimensions. So I'm trying to track a sine wave at 2 radians per second. Yeah, it looks like it's about locked onto it. Got it. Notice the beam is leaning. That's not my control output. The lean is whatever it takes to make it work. What I'm controlling is position. And the position is going back and forth at 1 radian per second. So it is working. And that's when my set point is sine of 2t. And see, there it's tracking. Green is the set point, blue is the output. Let's change it. Let's make the input cosine of 2t. So it starts at 1, it comes back. It's a little bit high. Looks like there's tracking. If I look at the response versus time, it's tracking. I can show that I can reject a disturbance. To make the set point 0 and add a disturbance, and it's really hard to see. Let's make the disturbance bigger so you can see it. But here my set point is 0, my disturbance is 50 sine of 2t. It's something big enough I can see something happening. Here's what I get. I've got a disturbance that's pushing it back and forth. My set point is 0. I want it to be sitting at the origin in spite of that disturbance. So what the integrator is doing, the servo compensator, it is trying to figure out the sine, cosine, how much is sine, how much is cosine, what's the amplitude, whatever it takes to cancel the disturbance, and it's trying to figure it out, and looks like it's just about figured out what I need to apply to cancel the disturbance. Then the output tracks the set point, which in this case is 0, meaning I'm rejecting a sinusoidal disturbance. This also works when you put the two together. I can reject a disturbance at 2 radians per second and track a sine wave at 2 radians per second. So the servo compensator does both. We'll add a plot, and there it is. Eventually it figures out what it takes to force the output to 0. Note, however, there's a slight problem with this. I'm assuming the disturbance is at 2 radians per second. If it's not, like suppose it's equal to 1 radian per second. Again, this isn't going to work. The reason being is the servo compensator has infinite gain at 2 radians per second. It's designed to track a 2 radian per second set point. If the set point is a different frequency, it's not designed for that. The gain is no longer infinity. It's no longer going to track. So at 1 radian per second, it no longer works. If you do want to track a set point that's at 1 radian per second, that's a complete redesign. I need to come up with a new servo compensator dynamics. I need to come up with new feedback gains. Complete redesign of the system. So that's a servo compensator with a sinusoidal set point. What we'll look at next is what happens if I have both a constant and a sinusoidal disturbance. That'll be the generalized servo compensator. That'll be our next lecture. With this system, if you apply a step input, it won't track. Again, it's not designed to track a constant, it's designed to track a sine wave. If I give it a different frequency input, like DC, it'll do something, but it won't track. That'll be our next lecture, generalized servo compensator. If I have multiple frequencies, such as a constant and a sine wave. That's lecture number 17, servo compensators for AC inputs, for ECE 463, modern control.